By the end of this video, hopefully you'll be able to find the interior angle sum of this star. Sometimes generalizing or abstracting in mathematics, or solving any problem for that matter, helps create a clear picture without the clutter of calculations. Let's consider a compact, path-connected subspace of the plane R2 with trivial fundamental group, meaning there are no holes. And finally, we want the boundary of the space to be a simple closed curve, otherwise known as a Jordan curve. We'd like to look at what happens to the number of regions as we make arbitrary straight cuts. We made 4 cuts and produced 9 regions. You see that it is hard to control the number of regions produced by a certain number of cuts. So let's limit ourselves to simpler cuts. Cuts like this one are a no-no. Here are due to 2 conditions. Number 1, the cut line must be contained completely within the interior of the space, except for the 2 points on the boundary. So there can only be 2 points of intersection with the boundary. And 2, the cut line cannot intersect any other cut line within the interior of the space. Okay, let's make some simple cuts. Okay, this is good. It cuts into 2 regions. This cut is good too. We have 3 regions. Uh-oh. This cut is not good because it intersects with the last cut line. Okay, this is good. Now we have 4 regions. And 1 more. Now we have 5 regions. So 4 cuts produced 5 regions. It seems in general that n cuts would produce n plus 1 regions when we cut in this manner. Now let's try to prove n simple cuts will produce n plus 1 regions. This is essentially an induction argument, but not typically. The hardest part is the base case. Do you see why this is? Pick a point on the interior of the space. Since the space is compact, there exists a circle of some diameter that covers it, with the interior point as the center of the circle. By the Jordan curve theorem, the diameter, acting as a cut line, will intersect at least 2 points on the boundary. Pick the 2 closest points with the red point contained in the line. This cut is contained entirely within the interior, and the endpoints lay on the boundary, thus is a simple cut. Once this slice is made, this arbitrary space is cut into 2 regions, each of which is just another space with the same properties to be able to cut into 2 regions themselves. Now let's apply this logic to a convex polygon. As mentioned prior, the idea is to dissect the polygon into smaller regions by making appropriate cuts. We want these regions to be triangles because we already know the interior angle sum of any triangle is 180 degrees. The question is exactly how many triangles are being produced. Here we have a pentagon, thus it has 5 angles, and 1, 2, 3, 4, 5 vertices. We can pick a base point, say the red point, and make a cut through one of the other vertices. Now let's make another one. We made 2 cuts through 2 vertices, producing 3 triangles. 1, 2, 3. Notice that we did not draw lines to 3 of the vertices. Is this way unique? Is there another way to construct triangles? Well, as long as the cut line stays inside the polygon and does not intersect any other line within the interior, we can do it. Here's another choice. We have 1, 2, 3 triangles. What about this line? Is this okay? Well, look at the yellow highlighted angle. It does not contribute to the measure of any of the interior angles. Thus, we see why we do not want the cut lines intersecting in the interior of the polygon. So, we cannot make this cut. Finally, we can calculate the interior angle sum of a convex pentagon, which has 5 sides, and we produce 3 triangles. So we have 180 degrees plus 180 degrees plus 180 degrees equals 540 degrees. Now let's look at a 7-side convex polygon, otherwise known as a heptagon, though the name is not so important. This isn't biology after all. 7 angles. Now let's draw the lines to the vertices. 1, 2, 3, 4. This makes 5 triangles. Notice the constant. We did not draw lines to 3 of the vertices. We made simple cuts through only 4 of them. Summing up the angles, we obtain 900 degrees. From the previous examples, perhaps we can make a conjecture. Maybe for any polygon, or at least a convex polygon, the interior angle sum is 180 degrees times n minus 2, where n is the number of sides of the polygon. Now let's try to prove that the interior angle sum of any n-sided convex polygon is 180 degrees times n minus 2. We make our interior angles and n vertices, 1, 2, 3, 4, n minus 2, n minus 1, and n. We pick a single base point, which is only always possible in the convex case, and we'll pick the red vertex as our base point. We make simple cuts to all the vertices except 3 of them. So how many cuts did we make? It is equal to the number of vertices we drew to, which is n minus 3. But n minus 3 simple cuts produces n minus 2 regions, because we have n minus 3 plus 1 equals n minus 2. And what is the geometry of each of these regions? They are triangles with 3 vertices, the base point, and 2 adjacent vertices of the polygon. This might seem trivial, but when you have a polygon with 1,000,000 sides, counting in an organized fashion is paramount. I want to show you guys a portion of what Khan Academy did for their explanation of the interior angle sum theorem.
Let's say I have an S-sided polygon and I want to figure out how many triangles, non-overlapping triangles that perfectly cover that polygon. How many can I fit inside of it? And then I just have to multiply.
This is not quite correct. The condition of overlapping is not enough. He is missing the idea of triangulation of a polygon. We also need that the vertex of each triangle match up with some vertex of the polygon. For example, this pentagon is not triangulated. Some of the vertices of the triangles do not match up with the vertices of the polygon. And because of that, these angles do not contribute to the interior angles of the pentagon. Here's another issue with this proof.
Of the number of sides. So once again, 2 of the sides, or 4 of the sides are going to be used to make 2 triangles. So there's 2 sides right over there, and then maybe we have 2 sides right over there. I can draw 1 triangle over, and I'm not even going to talk about what happens on the rest of the sides of the polygon. You can imagine putting a big black piece of construction paper. There might be other sides here. I'm not going to worry about them right now. So out of these 2 sides, I can draw 1 triangle just like that. Out of these 2 sides, I can draw another triangle right over there. So 4 sides used for 2 triangles, and then no matter how many sides I have left over, so I've already used 4 of the sides, but after that, if I have all sorts of craziness here, I could have all sorts of craziness here. So let me draw it a little bit neater than that. So I can have all sorts of craziness right over here. It looks like every other incremental side I can get another triangle out of it. So that's 1 triangle out of there, 1 triangle out of that side, 1 triangle out of that side, 1 triangle out of that side, and then 1 triangle out of this side. So for example, this figure that I've drawn is a very irregular one.
He shows a non-convex polygon as if he is trying to prove the general case, but he presents non-convex polygons as if they all have this fan structure, which means we can always pick a base point and join every vertex, except the 2 left and right, of the polygon from that one vertex, but this is false. What is the minimal polygon for which one cannot triangulate the polygon from a single vertex? Again, when the polygon is convex, we can always find such a base point. So we will be looking at only non-convex polygons. Let's look at the first case of a triangle. It has 3 sides, therefore it's already triangulated, so that doesn't work. What about 4 sides? We pick a base point and draw a line. This triangulates the quadrilateral, so that doesn't work. What about 5 sides? Again, pick a base point and we can draw 1 line and then another line. This triangulates the pentagon with 3 triangles, so no, this doesn't work. What about 6 sides? A non-convex hexagon. In this picture, these 3 vertices are collinear, and then this is necessary. We're going to pick a base point and go 1 by 1 and check each vertex. Let's pick this one. We can draw a line here and a line there, and that's it. So we get 3 regions. 1, 2, 3. So that works. Good. We cannot triangulate it from that base point. Okay, let's pick another vertex. Okay, we can draw 1 line and another line, and it looks like we can't draw it to any other vertex. So we get 1, 2, 3 regions. Good. So we cannot triangulate the hexagon from that vertex. Pick another vertex. We can't draw a line anywhere from here, so we can't triangulate it. Pick another vertex. We can't draw a line anywhere from here either, so we can't triangulate the hexagon. What about this one? This one looks like it might be promising. We can draw a line here, and then look, we need these 3 points to be collinear, or the middle one to be indented more, because it is possible to draw the one in the corner, a line from the vertex in the corner to the one down there. So we need them to be at least collinear. Okay, and then we can draw a line there, but we cannot triangulate this, so this works. And leave it to you to check that the last one, you cannot draw a line to any vertex either. So it works. Therefore, we have showed that the non-convex hexagon is the minimal polygon that cannot be triangulated from a single vertex. However, we can still triangulate this non-convex hexagon with 2 vertex. We can pick a vertex point here, and then we can draw a line here, a line here, and a line here. We've broken up into 1, 2, 3, 4 regions, which are all our triangles. Notice that all the yellow angles of the first triangle contribute to the interior angle sum of this non-convex hexagon, as so do the green angles of triangle 2, so do the purple angles of triangle 3, and so do the white angles of triangle 4. To sum things up, here's an important theorem that concludes the general case of the interior angle polygon sum theorem. Every simple polygon, convex or non-convex, can be triangulated, more specifically into n-2 triangles. I should mention one last thing. These questions that I was asking and this minimization I was exploring about the number of base points is actually equivalent to the art gallery problem posed in 1973. Here's the paper/presentation I stumbled upon. So what this means is for the art gallery problem, you would need 1 guard to watch over this whole gallery, you would need 1 guard to look over this whole gallery, and you would only need 1 guard to look over this whole gallery. But for the 6-side figure, you would need 2 guards to look over the gallery. This is a circle. It is one-dimensional. This is a disk. It is two-dimensional. This is a polygon. It is one-dimensional. This is a polygon region. It is two-dimensional. After thinking about it more, the triangulation problem through some number of the vertices is not exactly equivalent to the arc gallery problem. In this example, I have these three vertices collinear and these three vertices collinear. That is not enough. As I alluded to earlier, you need to indent two of them. You only need one guard to view this whole gallery, actually, because we can have a triangle here, a triangle here, and a triangle here. But as mentioned prior, this is not a triangulation. In fact, you could also place a guard here and a guard here, and it would also work as a single vertex. So we need to indent them more. We need to indent this vertex and indent that vertex. And now it will work, because this vertex cannot see that vertex, this vertex cannot see that vertex, and this vertex cannot see that vertex. Now we need two guards. If you enjoyed watching this video, hit the like and subscribe button now. Also, check out my book, Learning Isn't Linear, on Amazon.com. If you saw any mistakes in the video, please leave a comment about it. My hope is that teachers will be able to implement some of these ideas in their classroom. And finally, remember, prioritize long-term learning over short-term test taking.